Alright, so before we carry on with our new topics, over my quick break here, I've kind of solved the questions I had previously, so I want to just share some of the I'll answer some of the questions I had before with you. So we're going to be solving So first off, before we mentioned that the group GR alpha of G is abelian, and I wanted to know why. Well, it turns out, so a group is abelian if the commutator is always equal to 1, right? Right here on the side, I'll make a side note. A group is abelian if xy equals yx for all x and y. And we can multiply the left sides by x inverse and then y inverse to get that the group is abelian if the commutator of two elements is always 1. And so GR alpha of G is going to be abelian if the same condition always holds. But we know that omega of x, y is greater than or equal to omega of x plus omega of y. And since x and y are in GR alpha of, or in our case, they're going to be elements from, say, G alpha, or informal. This is going to be at least alpha plus alpha, which is, as you may know, greater than alpha, since alpha has to be greater than 0, which means for all x, y, and g alpha, x, y must be in G alpha positive, and therefore the image of x, the commutator, in GR alpha G is equal to 1. And so this is what gives us that GR alpha G is abelian. The other question I had, I'm using Roman numerals here, I kind of glaze over what is the algebra structure, the algebraic, maybe it's not a great way of phrasing it, on GR of G. Like, I know it's an algebra, but how does addition, essentially how does addition and the Lie bracket work, were my questions. So keep in mind, for all x bar in GR alpha of G, each constituent, x bar, what is x bar really? X bar is equal to some x plus, that's a terrible plus all of G alpha positive for some element x in G alpha. So x bar plus y bar is equal to this is just the image, I believe, of our group operation. So this is just xy, which is equal to xy plus g alpha positive. I'm going to say x and y are both in g alpha. If they're not, then essentially they're in different subsets of that direct sum we have, and so they just like don't interact, they just slot into different components. And as we saw before, the bracket between two elements, I don't know why I'm using this awkward bar notation, but anyways, the bracket, as we saw, is just the commutator of x and y plus g plus alpha plus beta. This time it's for x in g alpha, y in g beta. And keep in mind, I am like, this is all, I'm still like learning this, so this is all not as formal as the rest of this will be. So like, don't take my word for any of this. But this is my current analysis of like the situation. Now that we've got that out of the way, let's pick up from where we left off last time. So our next construction, we've got a filtration on a group. Now we're going to work with integral filtrations of groups. So this is a proposition. For any group G, there is a, this is horrible, there is a one-to-one correspondence between the two following things. On the one hand, we have filtrations, which, as we defined before, is omega from G to R with this additional positive infinity element for the identity. And these are going to be integral filtrations. That is, the image of our group, when it is a real number, is going to be a natural number, as you would expect. Not as you would expect, that is something you explicitly have to construct. And our second condition is decreasing sequences, and these are going to be subgroups of G indexed by the natural numbers. And these are going to be subgroups such that, first off, G of 1 is just going to be the entire group. So that's our first group in the sequence, is going to be the entire group. And second is that the commutator of two of the subgroups, so Gn and Gm, is going to be contained within the subgroup indexed by n plus m. Now, if you've taken a group theory class before, you may have seen like the central series, I believe they are. Yeah, the descending central series. And we're going to tie this construction back to that pretty soon. Okay, so the first one, if we have the first one, we can construct the second one in, it just says is clear. And so I think the idea is that you just let Gi be equal to the elements of our group such that their image under our integral filtration is at least I. So since you can see by their definition of the integral for filtration, the image of anything has to be at least 1, so our first group is going to be the entire space, and going on from there we are going to get our second condition based on the properties of filtrations as defined before. And so the second direction is the more interesting one. And I have to find my place. So we're going to let x be an element of G. And we need to eventually, so we have this decreasing sequence and we need to define a filtration. Define a filtration omega by omega of x is just going to be the index of the largest G that contains our element in question. So essentially that's what a filtration is, what an integral filtration at least is when we get down to it. It's keeping track of like how far in our decreasing sequence does this element of the group go. Now, obviously every subgroup of a group G has to have the same identity. So we have that omega of 1 equals our positive infinity. And because our first definition here, that G1 has to be G, then we get the condition that Wx is at least 1 for all x. And we also get that omega of x, because it is a subgroup, has to be closed under the inverse, and so it has to contain the inverse. Now, let omega of x be equal to n, omega of y be equal to m, and so x is going to be in at most in exactly Gn and not Gn minus 1. I mean plus 1. And y is also going to be in the set Gm minus Gm plus 1. And without loss of generality, we're going to let n be bounded by m, so that g of m is contained within g of n, and this gives us that x times y inverse is contained within Gn, which is equivalent to saying, my line's going to get kind of messy here, but that omega of xy inverse is bounded by the infimum, or I guess I'm going to keep my writing consistent, the minimum of omega of x and omega of y. I tried to fix my y and it did not work out. And we also have, as I mentioned before, that, maybe I didn't mention this before, but we also have that omega of x and y is at least the sum of omega of x plus omega of y, and that is all of the conditions we need for this to be a filtration. I mean, and this final condition, I mean, this is just basically an instance of this second condition of the commutator subgroup of Gn and Gm being inside Gn plus m. As I mentioned before, there is a very obvious example of this, which is the descending central series, which I hope you have seen before. Quick reminder, we define G1 equal to be G as you must, and we're going to define G of n plus 1 to be the commutator subgroup of G and Gn, and this is going to work inductively. Then we pretty clearly have Gn. If you scroll up, we see that this is going to obviously satisfy these conditions, and so this is going to be a decreasing sequence so let's verify this. Condition 1, as we saw, is just G1 equals G, so we literally set G1 to be equal to G. And our second condition here is be inductive on the bracket of Gn and Gm over n. So our base case, when n equals 1, then the bracket, the commutator subgroup of G1 and Gm is going to be G and Gm by definition. That looks like a C. And then this is going to be equal to Gm plus 1 by definition, so this is clearly contained within Gm plus 1. Now, for the inductive case, we have that the bracket, the commutator subgroup of Gn and Gm, well, this is going to be gn. We can expand out to be g and gn minus 1 with gm, which, as we saw before, is going to be inside the product of g and the gn minus 1 with gm, and the other version is gn minus 1 with g and gm. And by induction, this one on the right resolves to g n minus m plus 1. And this one on the right, keep in mind, we're keeping m fixed and we're inducting over n. No, never mind. This is actually just the definitionally going to be gm plus 1. We don't even need to go through that. And so this one, by definition, is going to be gn I. One second, sorry, I mixed up my signs here. This is going to be gn plus m minus 1. So this is going to be gn plus m trivially. And this one is going to, by induction, once again, be gn plus m. And so this is all contained inside gn plus m, so we have condition 2 satisfied. Now, note. If we have some decreasing sequence h, be a decreasing sequence of g as from before, then we're going to have that hn. I guess I should not use up a full line for this. Then hn is going to be inside of the nth term of the descending central series. And now keep in mind too, water bottle made a funny noise there. Keep in mind that with that, we're also taking the assumption that the first term is all of g. If that isn't satisfied, it's only going to make it smaller, so we don't even actually need that condition. So we can just work with the inductive case to prove this. So h to the n plus 1 is obviously going to be inside of h1, hn, which by induction is going to be inside of g1, gn, which is equal to gn plus 1. So our descending central, what this means is our descending central series is in some sense like the slowest, the most broad possible version of the central series, so it's going to give us the broadest possible filtration. And also, we can define the descending central series for any group pretty obviously, so it means we can always find at least one, too. That's kind of nice to know. Alright, there is one more topic we have listed here, gonna be honest, looks kind of scary, but we will persevere. This one is going to be filtrations in the general linear group. I believe n is supposed to be the dimension, so I'm going to write it as what do you call little letters on the bottom? I used to know that name. It's bugging me. Alright. So, we're just gonna kind of dive into it. Let's see if we can follow along. F, B, a field, of course, with, and here's where it starts getting complicated, ultrametric absolute value. And so essentially that's just an absolute value, which kind of intuitively kind of looks like the p-adic absolute value. So it just satisfies a slightly different condition than the normal metric. I don't remember what it is off the top of my head, but I know how it works intuitively. We're going to let AV be the ring of V. Oh, be the ring of V. So this is V is coming from this ultrametric absolute value of some sort. This is like the valuation, I'm thinking, maybe. Don't take my word on that. I'm going to let MV be the maximal ideal of AV. And then, of course, we're going to take the quotient with F, V being set equal to the ring of V, quotienting out its maximal ideal. Let n be a natural number and we're going to let G be the group of n by n matrices with coefficients inside of AV such that G, this term G here, this matrix G is going to be isomorphic to 1 mod MV. So essentially, the image of this under the quotient map is going to be the identity map in F of V. And they have the example that if we write G through its coordinates, then we have that the ijth coordinate is going to be equivalent to 1 if they match up and 0 if they don't. And that is once again under modulo MV. So if G is element of the group G, so that is G, lowercase g here, is a n by n matrix with coefficients in AV whose image in FV is 1. then we have that G is going to be equal to 1 plus the kind of plus it's a representative of X, where X is going to be an n by n matrix, of course, and its coefficients are going to be drawn from the quotient MV. Essentially, we're splitting up our element from the matrix to its image, which we know is 1, and the what's getting thrown away, which is X. And we have, how do we know G is a group? G is a group as it is the kernel of a homomorphism from the general linear group of n by n matrices over AV to the general linear group of course, dimensional n of this new f of v, where this map is of course just going to be the quotient map over each of our coefficients. Now, we're going to take X to be an n by n matrix over F, with its elements being xij. And using this, we're going to define v of x be just the smallest image of its components under our map V. And this is going to give us our filtration. So we're going to define our filtration G to the reals adjoin plus infinity. And we're going to define it as omega of some element G from our group is going to be this map V of x with, as before, where x is the cast off essentially as a quotient map of G. Now, of course, we have the natural question: is this map a filtration? The answer better be yes, otherwise I don't know why I did all this. So, omega of 1, what is that? Well, in that case, x is going to be 0, which by how the ultrametric works, that is going to be v of 0 positive infinity. And of course, we also have that omega of every element is going to be strictly greater than 0. We're going to let G lambda be, as always, our level set. Not level set, it's, we're going to be cutting off. G has to have a filtration of at least lambda. And we're going to let A lambda be x such that an element x elements x of f such that v of x is once again at least lambda. So then we can see that GL is the kernel of the canonical homomorphism from GLN of AV to GLN, keep in mind these are the groups, GLN of AV over this A lambda, where this morphism is of course the quotient map. Hence we have that G lambda is a subgroup of G. Now, and this is our third condition. Where were these conditions? Oh yeah, okay. So, all that's left to show I guess I should write that down. All left to show is that the commutator subgroup generated by G lambda and G mu is inside of G lambda plus mu. So we're going to let G be an element of G lambda with G equal to 1 plus X. And similarly, we're going to let H be inside G mu with H equal to 1 plus Y. And so we need HG to be equivalent to GH under this mod G lambda plus mu. And we have that HG is equal to, we can just FOIL out the product Yx and GH. We're going to get the same thing, except the order of the last term is, of course, swapped. As the coefficients of x, y, and yx are in A of lambda and mu. Reminder, that means that V of them is at least lambda plus mu. And this means they have the same image. Essentially, this part x, y, yx is the part that doesn't commute directly, but since they both have a filtration of lambda plus mu, they will get sent to the same place in GLN of AV over A lambda plus mu. And so are congruent, I guess, is the technical term for it. mod g lambda plus mu. And that is how we get a filter, I guess, on, that is an example, at least, of a filtration on GL of n. And that is the end of that portion of the lesson. It's not quite been the full length of a video that I would like, but I don't know if I really want to commit to starting the thing there, because that's such a clean ending. Let me check real quick what we're going to be talking about next. Yeah, it's extensions, semi-direct products, and change of base ring. I guess I will just make a quick note of what we will be covering tomorrow. Hopefully that'll give me enough time to feel justified in cutting off this video. And then I'm going to end the video here. So next time, what are we going to be covering? We're going to be extending groups, extending algebras. We're going to be taking the semi-direct products, and we're going to be looking at change of base. I don't know if this will all be one session or not, but these are the upcoming topics, and after that we're going to start getting into in developing universal algebra stuff and get into some of the more heavy stuff. So this is just kind of pointing out, we're ending kind of the easier content, I think, to some extent. This is all kind of warm-up stuff, hopefully. I mean, this session here is maybe a little more intense, but